Imagine a world where artificial intelligence doesn't just mimic human thought, but learns to reason like a human, step by step, with clarity, logic, and even self-correction. This isn't science fiction. It's the frontier of next-generation AI, and it's being driven by a revolutionary approach called reasoning decomposition. At the heart of this transformation is a simple but profound idea. Instead of asking an AI to jump straight to an answer, like solving a complex math problem or diagnosing a rare disease, we teach it to break the problem down into smaller, manageable steps. Think of it like teaching a student not just to memorize formulas, but to walk through the logic of a proof, checking each step along the way. So how does this work in practice? Let's dive into the mechanics. Modern large language models are powerful, yes, but they often suffer from a critical flaw. They're prone to hallucination. They generate plausible-sounding answers that are factually wrong, especially when dealing with complex or unfamiliar tasks. Why? Because they're trained to predict the next word in a sequence, not to validate their own reasoning. Enter reasoning decomposition. The key innovation isn't just breaking problems down. It's making the AI show its work in a way that's structured, traceable, and self-verified. Take a classic example, solving a multi-step algebra problem. A traditional model might output, the answer is 7. But with reasoning decomposition, the model is prompted to generate a step-by-step chain of thought. First, simplify both sides of the equation. Then, isolate the variable by subtracting 3x from both sides. Now divide both sides by 2. Therefore, x equals 7. This isn't just a narrative, it's a formalized reasoning trace. And here, where it gets powerful. We can now evaluate the correctness of each step independently. If step 2 contains an algebraic error, the model can catch it, either through internal consistency checks or by using a secondary verifier model. But the real breakthrough comes when we embed this process into the model's architecture itself. Researchers at Google DeepMind, OpenAI, and others have developed models that don't just generate reasoning traces. They learn to generate them. How? Through a technique called self-consistency and chain-of-thought prompting. In chain-of-thought prompting, the model is explicitly instructed to think step by step before answering. But the most advanced systems go further. They generate multiple reasoning paths, evaluate them for internal consistency, and then select the most coherent one. For example, in a complex diagnostic task, say, identifying a rare genetic disorder from a patient's symptoms, instead of giving one answer, the model might simulate 3 different diagnostic hypotheses, each with its own chain of reasoning. Then it compares the logical structure, checks for contradictions, and aggregates the evidence to arrive at a more robust conclusion. This isn't just about accuracy, it's about transparency. When a model explains its reasoning in a structured way, we can audit it. We can see where it went wrong. We can trace back errors. And we can build systems that don't just predict, but justify. Now let's talk about the technical backbone. How do we train models to reason like this? It starts with supervised fine-tuning on reasoning datasets. These are large collections of problems, math puzzles, logical reasoning challenges, scientific reasoning tasks, each annotated with detailed, correct step-by-step solutions. Models are trained not just to predict answers, but to reproduce the full reasoning trajectory. But even better, reinforcement learning from human feedback, RLHF, is being adapted to reward not just correct answers but well-structured, logically sound reasoning. In some setups, human reviewers don't just score the final answer, they rate the quality of each step in the chain. This teaches the model to prioritize clarity, consistency, and logical flow. And then there's the emerging frontier, reasoning with external tools. Imagine an AI that doesn't just think, it calculates, searches, and queries databases. A model might say, I need to verify this chemical reaction. Let me run a simulation in the molecular dynamics engine. Or, I'll look up the latest clinical trial data on this drug. This is where reasoning decomposition becomes a pipeline. The model decomposes the problem, decides which tools to use, executes them, interprets the results, and integrates them back into its reasoning. It's not just thinking, it's orchestrating. But why does this matter? Because real-world problems aren't clean. They're messy, ambiguous, and often require synthesis across domains. A model that can decompose a medical diagnosis into biological, genetic, and environmental factors, then reason through each in turn, doesn't just give answers. It provides insight. And here's the most exciting part. This approach is already outperforming traditional models on benchmarks like math, GSM 8K, and Big Bench Hard. In some cases, accuracy has jumped from 50% to over 85%, not by memorizing more data, but by reasoning better. So what's next? We're moving towards self-improving reasoning systems. Models that don't just follow a fixed chain of thought, but dynamically adjust their strategy based on uncertainty. They might say, I'm unsure about this step. Let me reevaluate my assumptions. Or, this approach isn't working, let me try a different decomposition. This is the dawn of AI that doesn't just know, but understands. And it all starts with one simple principle. Don't ask the model to leap to the answer. Teach it to walk the path. Because in the end, the most powerful AI isn't the one that speaks the fastest or remembers the most. It's the one that thinks the clearest. The future of artificial intelligence isn't just smarter, it's more thoughtful. And as we continue to refine how models break down problems, trace logic, and verify their own work, we're not just building better tools. We're building systems that can truly reason. And that changes everything.